Now in this video we'll be starting off with trigonometry and trigonometric functions. So however, in the previous video I had given you a question as to express the number of diagonals, to find the general term for diagonals of a k-sided polygon. So if you found patterns, there are two mistakes that I made. First of all, I had to define what a diagonal actually is. A diagonal is any line segment. It is any line segment that joins non-adjacent vertices of a polygon. Anyhow, so this is the definition, and I hope that maybe you went on the internet or use some LLM, chat GPT maybe, to find what a diagonal is. And the second mistake that I made is that to assume that there might be a pattern to the pattern that you can establish by writing out the number of diagonals. Actually, it's pretty complex. So I'll just give you the answer, and if it is too complex, then you can avoid it. And however, if you're inquisitive, then maybe you can go on ChatGPT or Gemini and maybe try to learn more about the function that I'm going to tell you. So first of all, there is something called as factorial. N factorial means the product of all numbers from n till 1. So 3 factorial would mean 3 into 2 into 1 and so on. 4 factorial similarly is 4 into 3 into 2 into 1 and so on. Second is the combination function, NCR, which is n factorial upon n minus r factorial into r factorial. To calculate the number of line segments between n collinear points, n non-collinear points, coplanar but non-collinear points, is given as NC2. Again, the number of line segments that can be drawn between n non-collinear but coplanar points, as in our case, is given as NC2, right? So now NC2 is essentially n factorial upon n minus 2 factorial into 2 factorial. N factorial can be rewritten as n minus 1 n minus 2 factorial upon n minus 2 factorial into 2 factorial. So this gets cancelled out. So it becomes n into n square minus n by 2. Now you would observe that among the line segments that can be drawn between these non-collinear points, let's say you take a pentagon, right? Let's say these are the vertices and you draw line segments between them. Now among the diagonals, which I am drawing with the yellow line, there are also the sides which gets counted into the function that I have written, or the expression that I have written. So you need to subtract the number of sides from this expression to get the number of diagonals. So all in all, your expression becomes n square minus 3n by 2. I know it might be a bit too intimidating for our discussion at this point, but just to make you familiar maybe with higher concepts, or let's say if you are more inquisitive, then definitely I would advise you to look up the chapter of permutations and combinations in maybe class. There's the chapter in class 11th or in the competitive exam module maybe. But yes, or if you are unable to find on the platform, then obviously you can just Google it or GPT it maybe. So yeah, now let's move on to the relevant things for this topic of triangles. Second, so trigonometry is essentially the relationship between the sides, between angles and sides of triangles, and with a particular importance of right angle triangles. It is used to measure the heights, the distances, and is applied to a broad range of topics. Historically, it was used to build the pyramids. By the Egyptians, they used an instrument called a seked. The Babylonians used trigonometry in some cases. Then there is the famous Plimpton 322 tablet, which gave the list of Pythagorean triplets. Then we have our Indian mathematicians as well. Aryabhatta gave an equivalent to the modern sine functions. Brahmagupta gave modern or the complex algebraic identities. Bhaskara also contributed. So the contribution, so trigonometry is not a newfound mathematics. It is ages old, and this, the uniqueness of trigonometry is all the functions that we discuss in trigonometry are pertaining to triangles, right? So because trigonometry is so specific to right angle triangle, and it's it is easily explained for a right angle triangle. So I'll just draw up a basic right angle triangle and show you. Right. So right angle triangle is of the form like this. So one of the angles is a 90 degree, and obviously because the sum of the angles in the triangle are 180 degree, consequently these two angles, let's say the right angle triangle is the right angle is at angle B, then the angle A and C are acute. That is, they are less than 90 degree. Acute angles are those angles which are less than 90 degree, right? They have to be. It's an identity of some sort, or a necessity of some sort, that the other two angles in the right angle triangle have to be acute. Nevertheless, the side opposite to the 90 degree angle or the right angle is called the hypotenuse, and the other two sides are called the leg. Typically, you denote, although I have said that you denote the side opposite to angle A as small a, and the side opposite to angle C as small c. So by the same convention, the hypotenuse is equal to small b. Now, there is this famous identity by Pythagoras that in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the legs, or the other two sides, a square plus c square, right? In the books, it might be possible that you encounter, let's say, a square plus b square is equal to c square. So it's important that you don't get confused. You need to understand that what is actually we are referring to. In the books, it might so happen that instead of C, they have denoted it as B and the hypotenuse as C. But because I'm using this notation, and why I'm using this notation will be more clear in the future when I discuss sine rules and cosine rules, is I'll follow this notation always to denote the Pythagorean identity. And if I do not, then you should roll back the clip and try to find out what sides I'm actually referring to. It's always that the sum of the squares of the sides other than the hypotenuse gives us the square of the hypotenuse, right? Yes. So now we have discussed the Pythagorean identity. Now we can move forward. There is a few moments ago I said a term which is called our Pythagorean triplets. So these are essentially natural numbers that follow this identity. The common ones I'll give you. 5 square is 3 square plus 4 square, right? Then you have 12 square plus 5 square gives you 13 square. Now as a homework, I want you to find out the Pythagorean triplets till 10, the common Pythagorean triplets. Another thing you can also see that you just can simply multiply it with these triplets 3, 4, 5 by a natural number. Let's say I multiply all the numbers by 2, then you have 6, 8 and 10. This also forms a Pythagorean triplets. So these are kind of unique, that is the ratios are not divisible by a natural number. But yeah, if you can multiply it with a constant term and still get a Pythagorean triplet. Now let's move on to sine. Now sine of an angle. So sine is actually a function, but let's say I say sine x. What does it actually mean? X is an angle, and in later classes or in higher mathematics will modulate x as any real number, perhaps extend the concept to any real number. The domain of sine is any real number, but for this discussion on triangles, we will restrict it to some angles which are commonly found in a triangle. So sine of x is essentially the ratio between the perpendicular and the hypotenuse. Now what does a perpendicular mean? Perpendicular is specific to the angle that you are referring to. Say for C, the perpendicular is actually the side opposite to it, that is C, and hypotenuse stays the same, this B. However, for sine A, the perpendicular again becomes the side opposite to it, so it is A and the hypotenuse becomes B. I'll give you an example. I'll give you a practice problem. So consider this triangle ABC, right angled at B. Now I want you to give me the expression of sine x and sine y. Pause the video and take a minute. Sine x is basically 3.4 upon 2.1 and sine y is 6.1, 2.1, right? But my next question to you is that, is this a right angle triangle to begin with? You clearly can see that 6.1 square plus 3.1 square is not equal to 2.1 square. So it is not a right angle triangle, and sin x and sin y have no meaning there. I'll move a step further. Is it a triangle to begin with? There's a property in triangles that the sum of two sides is always greater than the third side, which we will discuss later. But in this case, you can observe clearly that the sum of two sides, that is 2.1 plus 3.4, is actually less than 6.1, and hence this is not a triangle to begin with. This triangle does not exist. It's an imaginary triangle. So often before solving a question, we need to establish whether it's actually the things that are present before us are actually real or not. Again, sorry, this thing happens over and over again. Yeah. Okay, no, I think this much space is enough. So I've introduced you the sine function. Then I'll introduce you to the cosine function. Sine function is often in textbooks you will find that it's denoted as P by H, that is perpendicular by hypotenuse. So perpendicular is always the side which is opposite to the angle. And for cosine is essentially the ratio of the base to the hypotenuse. Now base, well, the simple, as you might have figured out, it's basically the side we have been neglecting so far. So in this case only, cosine of A becomes the base, that is the side on which it is formed, which is C upon B. Hypotenuse remains the same, and cos C is A upon B. Right. As in homework, I want you to find out the value of cosine of B. Take this as a homework, right? In this triangle that I am referring to. Okay. Another function that I'll want to establish here is tangent or tan function. Tan is the ratio between perpendicular and base. So you have this triangle ABC. This is side A, this is side C, and this side B. Then tan of C is actually C by A, perpendicular by base. And similarly, tan of A is A by C. Again, as a homework, I want you to find tan of B. And this is the place where things get a bit messy. So let's stop it here. In the next class, maybe we can discuss the values of some values of trigonometric functions of standard angles.